For the second part of this module, we're going to be dealing with some Boolean algebra. It's pretty fun. It can be a little overwhelming at first, but it'll come to you, trust me. So let's talk a bit about digital inputs. So when we are building electronic circuits, we're using logic gates. And the idea is it's very similar to electric circuits. So if there is voltage present, you think of the wire being charged, something being on. If you flip a switch and voltage is not present, you think of it being off. And other ways we have of expressing that are true, false, closed, open, high voltage, low voltage, and what we'll use 1 and 0. Okay, voltage presence 1 and not present 0. So what do we do with that? We send this voltage through logic gates. So our three main ones that are going to alter our inputs are NOT, which is a single input gate, AND, which can be 2+ inputs, and OR, which is also 2+ inputs. We can take these gates, the AND or the OR, and also make them kind of NOT gates, like NOT AND or NOT OR, but we call that NAND and NOR. And then we have these other kind of stranger gates called exclusive gates, XOR, and what I call XNOR. So we have exclusive OR not exclusive OR. And everything you make can be created from a combination of these gates. So what am I talking about here? So let's say we have an input A. If we send it through a NOT gate, and we'll have another thing with all the gates on in the next page, a NOT gate looks like this. I'm going to label it NOT. When you send an input A through a NOT gate, what you get out is not A. We represent that in Boolean algebra with a little bar on top of an A. So that's a negation, or the inverter, if you will. So what that means is if I had a 1 coming into a NOT gate, my output is a 0. And if my input was a 0, my output is a 1. So whenever you do this, if A equals 0, you know that not A must be 1. And likewise, if A equals 1, then not A must equal 0. Looking at our logic gates that can have more than one input, here they are all written down. So we've already done NOT, and we're going to ramp it up. I strongly recommend that you have some kind of reference with you that has the pictures and what the algebraic expression, just until you get used to it. So the first one we're going to talk about is AND. It's not called a plug. This is my own reference when I was learning it to say, well, it looks like a plug. Okay, so AND looks like a plug when it has two inputs. It's a product gate. So the output is going to look like this. AB, you can have a dot in between to represent multiplication, but AB together, just like it would be in normal algebra, represents multiplication. And just like normal algebra, your output will be the product of all your inputs. So in this column, I've kind of got like combinations of inputs, and we're about to go through that on another slide. So what you can notice really quickly is that the only way with multiplication to output a 1 is if all your inputs are 1. The minute you multiply by 0, the answer you create is a 0, which is the same as saying your output will be a 0. The OR gate is a sum. It's like A plus B. So with this one, no matter how many inputs you have, as long as a single input is 1 rather, your output will be 1. Because the only way to get 0 by adding is to have 0 plus 0, or 0 plus 0 plus 0 plus 0. So the minute you have a 1 as an input, in both these situations, there's at least a single 1, your output becomes a 1. And if you look at this third one, you can be like, well, 1 plus 1 is 2. Well, in Boolean algebra, if it's not 0, it's 1. So if it's 2 or 200, it's actually 1. You only have two choices, 0 or 1. NAND is when you negate AND. When we do that, we have the negation bar across the top. And notice it's not just over one letter like the not would be. It's across the gate. So it's over the A and the B. And how do we represent that? We draw a little what I call a not dot on the front of our plug to symbolize NAND when we're drawing it. So the easiest way to do this is to build an AND gate for your inputs and then just flip them. So notice that down here, everything is the opposite of what it was for the AND gate. Likewise, NOR is the negation of OR. And see how the bar goes across everything here as well. I mean, it's like there's invisible brackets, but those can be understood. You take your vintage spaceship, that was your OR gate, and you put the not dot in front, and that makes a NOR gate. Same thing, looking at our OR outputs, we flip them. So if OR gave you a 0, NOR gives you a 1. If OR gave you a 1, NOR gives you a 0. XOR is a bit of a different beast. It has this crazy symbol, and it's not on here, but XNOR would be the same thing with the not dot, and it would look like I'm going to use this line to represent my XNOR because it's kind of weird. So there we go, XOR and XNOR. In the same way, XNOR will be a negation of XOR. Now, the way I explain XOR is if your output, and we're going to talk about sums because it's kind of got OR built into it, and that is a sum gate. So if you add things up and you get an even answer, like 0, then your output is even, 0. If you add things up and you get an odd answer, 1, then your output is 1. And these are the same as the behavior of the OR gate. Where it gets weird is when you get 2 1s as an input. 1 plus 1 is 2, that's even, so your output is 0 because that is also even. Another way to think of it is that if everything's the same, because you're only going to really have a 2 input XOR gate, then your output is 0. You have to have different inputs to create a 1 as the output. To hammer this home some more, we're going to look at all the possible outputs from different input combinations. For a NOT gate, remember that's this bad Larry, and a buffer is just if you don't flip it, it just goes through and stays the same. Your 2 inputs, you can only, well, 2 possible values for your input are 0 and 1. You have a single input, it can be 0 or it can be 1. And the NOT output will be 1. Buffer means just stays the same. If your input is 1, your NOT output will be 0, and your buffer would have just stayed the same. So let's look down here at our 2 input gates. Here's all I have A and B coming in to each of these gates. So A could be 0 and B could be 0. A could be 0 and B could be 1. A could be 1 and B could be 0. A could be 1 and B could be 1. 2 inputs, 4 possible combinations coming in. All right, so let's look at our AND gate. Remembering that it is the plug and it's a product. So to figure out what the output is for an AND gate, I just look at my 2 inputs. What's 0 times 0? 0. What's 0 times 1? 0. What's 1 times 0? 0. And what's 1 times 1? 1. Okay. The NAND gate is just the negation. So like I said, these tables that are giving us all the possible combinations are actually called truth tables, and we'll talk about that a bit more in a second, and we'll end up building a lot of them. But so our NAND gate is just the inverse, or not AND, so we flip everything. If AND was 0, NAND is 1. And I'm not looking back at A and B here, I'm just looking to one column over to figure this out. There we go. To build my OR gate, I'm going to look back to the A and B. And I have a hard time drawing OR, but it's the turbo spaceship. No, sorry, the vintage spaceship. There we go. So if A is 0, looking back over to here, if A is 0 and B is 0, OR will output 0 because 0 plus 0 is 0. Now for the rest of it, it'll be 1 because 0 plus 1 is 1. And 1 plus 0 is 1. And 1 plus 1 is 2, but in Boolean algebra, that is 1. 2 choices only. Our NOR gate is just a negation of our OR gate. So not even looking back to the left side, just looking right beside me at the OR gate and flipping all those values. XOR, adding that extra little line to make it into a turbo spaceship. A is 0, B is 0. Those are the same, and if I add them together, I get an even sum. So I have to have an even output. There we go. If A is 1 and B is 1, I add them together, get 1. That's an odd sum, so I want an odd output. Same with 1 and 0. But if I go down to 1 plus 1 is 2, that's an even output, so I want an even sum, so I want an even output. And then once again, if you're doing XNOR, just look to XOR and flip the values. A little more background information before we really get into this. Just like normal algebra, Boolean algebra has order of operations. It's not BEDMAS or PEDMAS. It's unfortunately BANAXO. So brackets, not, and, XOR, or OR. That's the order of importance. My son told me you could use BART needs actual xylophones, obviously, to remember it. I don't think that's particularly effective, but use what you can. And if you're not certain, you can always add extra brackets to signify what you're trying to do. But I do want you to be able to understand when you look at things that something might mean things in a different or particular order without having that crutch of brackets. So looking at a couple, I'm going to write down BANAXO over here. What comes first? So in number 1, what type of gates do I see? Let's talk about that. I see a NOT gate. I see an OR gate. It's very hard to not call that an AND gate. And here these are multiplied, right? So I also have an AND gate. And then looking over to BANAXO, most important, second most important, third most important. All right. So when you draw this, it'll look a certain way, or when you do a truth table for this, it'll look a certain way because of the order of operations. Number 2 is much more challenging. So in this situation, not only do I want you to know your things, but I also want to remember working inside out. I have a very, very long bar over a bunch of stuff. So that's going to be one gate made up of a bunch of different stuff. So I'm going to leave that because I know that will come at the end because it's like everything underneath is in brackets. So let's look to the actual brackets. So I see B or C, but it also has that negation. So I have a NOR gate. And I see here things are multiplied. So I have an AND gate. And it's not a NAND gate because the bar didn't end right here. It goes all the way across. So I have this XOR, but the bar goes all the way across, so it's negated, and it's an XNOR. Order of operations for this. Because the NOR gate is in brackets, it is more important than the AND gate. AND gate always before XOR, and the XNOR comes third. So it's really important to get your mind wrapped around that. A couple of slides ago, we were writing things down in a table, and we're definitely going to be writing lots of things down in very large tables because now we're going to start building truth tables. So they list all the possible input combinations, and then they show you outputs for whatever you're writing at the top of that column. So if you write not A at the top of that column, it'll show you the output for that. If you write a giant string of stuff, you're going to do some work and you'll get the output for a giant string of stuff. So when you build a truth table, generally we'll give you the input combinations, but you can, a general rule here is that the number of inputs you have is the exponent and 2 is the base. So if I have, remember we did the AB ones, if you have just AB, 2 inputs, 4 outputs. And right here we're saying if we have 3 inputs, which is as big as we're going to get, 8 outputs. Okay, we could use these truth tables to just test what's going to happen when we put inputs through gates or a circuit. And we can also use them to prove that Boolean algebra simplifications are equivalent, which is kind of the end goal of this unit. We're going to start by building a simple truth table from scratch. So before we look at our expression that we have to build the table for, see what all the possible outputs are, we have to list all our possible inputs. So like I said, generally we'll give this to you, but if we don't, it's pretty easy. So just take your A column. Either you count up in binary. The easiest, like if you're good at binary, you just start from 0 and count binary with 3 digits. But if you're not, that's fine. So we're just going to go put 4 A's as 0. So split it in half, right? Half of them are zeros, half of them are ones. And then do the same thing with the B's, except breaking it down more. So 0, 0, 1, 1, 0, 0, 1, 1. And then same with the C's, except just alternating 0, 1, 0, 1, 0, 1, 0, 1. And now we can go over to our expression and figure out what's happening when. So I'm going to write down my order of operations to have on the side. And I see that I have some brackets, and the brackets are dealing with an OR gate. I also see that I have an AND gate, but the OR gate will be given priority. So I have to get the output of the OR gate and put it with C into an AND gate. So we'll start by making a column that helps me figure out what's going on with that OR gate. I'm going to highlight the things that are going in just to make it a little easier. And I'm just going to look down those columns, doing the operation in each row. So for my first row, 0 plus 0. Answer is 0, output is 0. Second row, same. Third row, 0 plus 1 is 1. Fourth row, 0 plus 1 is 1. And we're just going to flip it, 1 plus 0 for the 5th and 6th, and still get 1s for the output. And for the 7th and 8th, 1 plus 1 is 2, which will be 1. And same for the last row. Okay, so I finished finding what comes out of that gate. Now I'm going to take my answer that I just found, and I'm going to put it into an AND gate with C. So this goes in as an input, and this line goes in as an input. And that's what I'll have. I'll have finished it. Okay, we're in an AND gate now, so we're thinking about multiplication. 0 times 0, 1 times 0. And I'm just looking across here. 0 times 1, 1 times 1. 0 times 1, 1 times 1. 0 times 1, and 1 times 1. So that's the final output. All the possible combinations giving all the possible values coming in for A, B, and C. Next, we're going to look at 2 more difficult expressions and circuits and how to do the truth tables for them. So I've preloaded this one with the inputs just to save a little bit of time. When I look at these ones, I mean, there's a lot going on, but what I see right away is that I'm going to use nots. These ones with just the bar over a single letter are not gates. So I always kind of write those down so I know that I have them for future use. It's easier to look to a not gate than to remember to flip it in your head. Trust me. Oops. Let's make it the right input. So I'm just taking that A column and changing the values over. Same with looking at that C column and flipping the values over. Okay. There's a lot going on. I'm going to deal with this first because it seems like less work. So that's an AND gate. It's not A and B. So looking, I'm going to use yellow for that. I'm going to use the not A I just made, and I'm going to use the B. I'm going to multiply them and write down the answer. This will be the output for that AND gate. And just the same thing. So I'm looking at the rows. 1 times 1, 0 times 0, 0 times 0, 1 times 0, and 1 times 0. Okay, done. Now, looking at the hot mess in the front. So I see that I have a bar across the top, so I know this is the negation. It's a negation of an OR. It's an OR. It is always easier in your truth table to build the OR gate, and then in the next column, flip it to do the negation. It's just way easier for your head. So what we're going to do here is we're going to look at not C, and we're going to look at B again. So it's the double stripe. This is an AND gate, so we're going to be adding our two values, our two inputs. So not C plus B is 1, and then it's 0, 1, 1, 1, 0, 1, 1. And now I'll take that next step and make my actual NOR gate. I look to here and I just flip the values. 1, 0, 0, 0, 1, 0, 0. I'm going to write an F for final answer in my last name because I don't feel like dealing with writing down the entire expression. So I need to deal with this column, and I need to do an AND gate with it and the other pink column. So I'm multiplying again. 0, 0, 0, 0, 0, 0, 0, 0. And all I have to say to this is, I made this myself, and I am not good at making up circuits that will do anything for you. Let's do a second one. It has less inputs, so we'll save ourselves a little work there. However, there's a little more respect for order of operations required. Before I even think about anything, I see that not B. I'm just going to throw a column that inverts B so I have it ready for something. I see brackets. I know those are the top priority, so I'm going to do this. And as I go further, I'm hitting the point where I'm just looking at A and not B, and if I see 1, I know that it's going to return a 1, right? Because it's that sum 1. I kind of just scan and go a little quicker. Now I have two choices for my next operation. I can either respect the XOR, or I can respect the AND before XOR. So I'm going to do that first. If I was going to do the XOR gate next, the expression would have to have brackets to tell me to prioritize the XOR. It doesn't. So I'm going to do this next. And in this case, I'm going to put some highlighting on. I'm looking here and I'm looking here. It's a product gate. So unless both inputs are 1, it's going to return a 0. I'm getting really quicker and quicker at this. Now I'm going to take A and I'm going to XOR it with this. So my inputs are this column and this column. So for XOR, if the inputs are the same, you return a 0. Or if their sum is even, you return a 0. So the first 3 inputs, the rows 1, 2, and 3, are the same it would have been with that OR gate. It's this row here that throws everyone for a loop. So be very, very careful. We've been building these truth tables without understanding what the things the schematic might be for these expressions or these circuits. Here's one. So to get an output that looks like this particular combination, a lot of 3 input AND gates and 4 input OR gates, this is what the picture might look like. And we are going to draw pictures, perhaps not this complicated, but we're doing it in a few minutes. But let's finish off by getting the truth table for this circuit. All right, preloaded for us. So here, just thinking about what we've got, we can do from the picture, but looking here, these are multiplication. So these are kind of their own distinct AND gates. 4 AND gates, and they're all going to go into an OR gate at the very end. So we can relatively easily do this, but first I'm going to write this down. I know people don't like it, but I speak from experience. Having that in a column makes a lot of sense. So let's negate A, and we'll negate B, and we'll negate C. Okay, so now we are going to make that first 3 input AND gate. We're going to look to here, here, here. Be lazy. The only way you're going to return a 1 in this gate is if all the inputs are 1. The only place that happens is right here. The rest of the outputs will be 0. All right, let's do it again. This time we're looking at A. I can't remember if I can write over. Yes, guy, cover it up. There we go. And not B. So looking at the green, and the only place we can return a 1, output a 1, is if all inputs are 1. And I see that happening here. And nowhere else. Okay. Here we go. Let's see if we can make some pinks. We need to change this to a pink. Oh, now it's just getting ugly. Sorry. And this bad Larry, I'm not going to cover over it because now I've almost made my original one invisible. Here we go. Okay, where do I have 3 1s in this combination? I know it's going to have to be down here. There it is. And I just knew that A and B were kind of 1 on these lower ones. And nowhere else will that happen. And our last and 3 input AND gate is just plain old ABC. So I'm just looking across these 3. Where do I get 3 1s? I can barely see it anymore. In my last row. This is starting to look like a total spaz thing, but it's not going to be, because we'll be able to recover it, because these are OR gates and those are the sum gates. So the minute you have any input being a 1, your output will also be 1. I'm just looking at these 4 columns, checking to see if there's any 1s, or you can go through and do it the math way like we were doing before, and that's what I get. So now we're going to look at pictures and create algebraic expressions from them. So you're definitely, like I said before, going to want to have a diagram or a little formula sheet, your formula sheet that shows you what all the various gates look at like. Okay, you can add extra brackets in this. If you're not feeling comfortable, just throw in extra brackets. I'll never mark you wrong if you have too many brackets, unless you're interpreting their location incorrectly. Okay. And just looking at the things that they want us to do, we're not going to worry about this yet. That's in the next slideshow. So here we have 3 gates. So I'm going to look at each one, and I'm going to call this one gate 1. So first thing I want you to do is identify what type of gate it is. It is a NAND gate. So you're going to look at what goes into that. And I always like to rewrite very close to the gate. A and B go in, and what is, you just got to get the expression from your formula sheet. What does A NAND B look like? It looks like that. Looking at our second gate, I'm going to switch some colors here. It's a NOT gate. C goes in, NOT C comes out. And now we're going to go to our third gate. We follow the wire along. We have NOT C coming in. From the top, we have A NAND B. And in the middle, it comes straight from plain old B. So we have a normal B, unaltered B coming in. This is an AND gate as well. So if we want to write this, gate 1, the B, and gate 3. So that is the expression for this circuit. If you felt uncomfortable, you could do this or add extra brackets, but this is good enough. Let's do another one. I see an AND gate, and I see my inputs are A as well as B. What does it look like when you have the output of an AND gate? It looks like that. I see a NOT gate here along the B line, so it changes the input to this second AND gate to NOT B as well as A. So the output for this gate is A and NOT B. Watching that you don't extend your bars too far. Finally, we're going to come to this OR gate. Our two inputs are A and B, as well as A and NOT B. So I write both those inputs down and give it the OR symbol. The very last one we're going to do for this set of slides seems complicated, but just work your way through. Let's see what's happening over here. We have A turning into NOT A, and it's going into this AND gate as a NOT A. This second input here, I don't want to do anything with it yet because it seems like it has to go through some other gates first. So I'll leave it alone for now. I'm going to start at B. I see that B goes both to this gate. I'm going to number these 1, 2, 3. I'm not going to number the NOT gates, 4, 5. So I see that B is coming in plain to gate 3 as well as to gate 1. And I see that C is coming in as is to gate 1. This is a NAND gate because of the NOT dot in the front, so remember to write it down properly. There we go. All right, and that B NAND C is going into gate 3 as the second input. So getting a little messy here, but trying my best. Coming out of gate 3, so that's going to go into gate 4, and it's also going to be the second input into gate 2. It's a very complicated one. All right, so now we have coming out of gate 2. We had our NOT A, and it's an AND gate, and you don't need to put brackets there. That is fine. Okay, going back down to the output of gate 1, because I need to get over to gate 4. So I'm going to have that B NAND C. I'm going to send it to a NOT gate. Now, that will come out as a double negation. And we're going to get to this a bit more with simplification, but that's the same as going back to B and C. So coming into gate 4, maybe some highlighting, we have this and we have this. And our output from gate 4, which is what? It's a XOR gate, will be B XOR BC. And because AND has higher priority than XOR, We don't have to worry about brackets for this one too. Looking back to the output of gate 2, now we have to take it and put it through a NOT gate. So that's the whole thing that gets negated. You can't just selectively bar it. You have to have what you had before, and then you negate the whole thing. All right. Our last gate is an OR gate. Our final output for this circuit will be disgusting. It would be a good kind of simplification. There's got to be a better way to build this and get the same outputs. Put your OR symbol, and then now the only thing I'm concerned about, I'm going to write down Banaxo because I see I have a XOR and an OR, and I want to make sure that XOR gets priority like it did in the diagram. 4 came before 5. 4 came before 5, pardon me. And this is fine as is. If you're not sure, you can add those extra brackets. So this is a killer one. If you can make your way through this, bravo.